BSc Chemistry IR Spectra presented by Dr. Giridhar M, Assistant Professor of Chemistry Department of Collegiate Education. So contents. In this session we will be studying types of stretching and bending vibrations, vibrational mode of polyatomic linear molecules, vibrational modes of polyatomic non-linear molecules, and applications of IR spectroscopy. Types of stretching and bending vibrations. Absorption of IR radiation causes bonds to stretch and bend. Stretching corresponds to increase and decrease in bond length within a molecule, and bending corresponds to increase and decrease in bond angle in the molecule. Stretching is of two types. So one is symmetric stretching, so as shown in the figure, symmetric stretching, and asymmetric stretching. So this is asymmetric stretching. And bending are also of two types. One is in-plane bending. In-plane bending can be scissoring and rocking. So these are in-plane bending. And out-of-plane bending. Out-of-plane bending is wagging and twisting. So these are the types of stretching and bending which takes place in the molecule on absorption of radiation. 1. So these are the selection rules. So let us see some example. So for linear molecules, the number of degrees of freedom, total number of degrees of freedom is given by 3n minus 5. So where 3n is total degrees of freedom, that means it contains vibrational degrees of freedom, rotational degrees of freedom, translational degrees of freedom. So here linear molecule, so if we place this linear molecule along z-axis, we see that the molecule can rotate like this, okay, along x-axis and also along y-axis, but on z-axis it is rotating along its internuclear axis, and therefore only 2 rotational degrees of freedom is possible. In case of translational motion, the molecule translational motion is nothing but kinetic energy. So the molecule can move from one place to another place. It is not like rotation. Translational motion is the molecule moves from one region to another region. So the molecule, if this is the point of the molecule, it can move in x-axis, it can also move in y-axis, it can also move in z-axis. Therefore 3 translational degrees of freedom will be there. So therefore vibrational degrees of freedom is calculated as total degrees of freedom minus rotational and translational degrees of freedom. So 3n minus 3 plus 2, 3n minus 5. So where n is the number of atoms present in the molecule. Say for example, if I take HCl, n will be 2 atoms will be present. CO2, carbon dioxide, 3. N value of n will be 3 because in this 3 atoms will be present. So let us take one example, that is carbon dioxide. Carbon dioxide is linear molecule. It's a polyatomic linear molecule. So for this 3n minus 5, that is 3 into 3, 9 minus 5, 4 normal modes of vibration will be present. So as I already told, n is the number of atoms. 4 normal modes of vibration, and these are shown in the image. A is called symmetric stretching, B is asymmetric stretching, C is symmetric bending, D is asymmetric bending, and A, it is symmetric stretching. Symmetric stretching does not produce any change in the dipole moment. So the dipole moment of this stretching is 0. The dipole moment of this molecule is 0. Even after absorption of radiation, it does not produce any change in the dipole moment, and therefore in the IR spectrum we see 3 peaks, one for Okay, asymmetric stretching, another for asymmetric bending, and another one for symmetric bending, and another one for asymmetric bending. So for nonlinear molecules, so it has 3 rotational degrees of freedom and 3 translational degrees of freedom. Therefore, vibrational degrees of freedom will be 3n minus 3 plus 3, that is 3n minus 6. 3n minus 6. So this is for water molecule. Water molecule has bent structure. So this is non-linear molecule. So for non-linear molecule, as I already told, 3n minus 6. 3 into 3 minus 6 is equal to 3 fundamental modes of vibration. We observe 3 fundamental modes of vibration. So here one is symmetric stretching, this is asymmetric stretching, and this one is bending. So 2 types of vibrational modes will be present. One will be symmetric stretching and bending. In stretching, symmetric stretching and asymmetric stretching will be there. In bending, we have different types of bending like scissoring, rocking, so etc. Therefore, there are 3 vibrational modes of water. So one appears at 3652 per centimeter for symmetric stretching, another at 3756 per centimeter for antisymmetric stretching, and 1595 per centimeter for symmetric bending. So lastly, application of IR spectroscopy. One, it is used in the detection of functional groups. To find the moment of inertia and bond length can be calculated. 3, for calculation of force constant it can be used, and force constant gives the strength of the bond. It can also be used in qualitative analysis, that is to compare the spectra of unknown compounds with the standard and identification of new compound. For quantitative analysis, impurity reduces the sharpness of the peak. So from the study of this peak, percentage purity can be calculated. So these are the some of the applications of IR spectroscopy. One is detection of functional group, detection of moment of inertia and bond length, calculation of force constant for qualitative and quantitative analysis. So these are the references. So thank you.